Welcome. So we've now gone through chapters 1, chapter 2, part 1, and chapter 2, part 2. And those three sections are going to be the focus of the first midterm. So this week, what we're going to do, like on Wednesday, we'll go over problem set number 3, which is over more naming stuff, grams to moles for compounds, and then also this empirical formula, molecular formula stuff. Next week, all right, what we'll do is we'll have the midterm exam. And the midterm is just a way for you to show all the stuff you've learned in this class, all right? And there's been quite a bit. So I'm hoping this will be just something to kind of show me what you've learned and stuff. Shouldn't be a big deal. But we'll talk about what's all happening. The midterm itself, again, the important part is that it comes out Wednesday night. So just like the quizzes and stuff you've been taking, Wednesday, 5 or 6 o'clock, exam 1 will be released on the internet. And then exam 1, like the quizzes, will be due Friday, 9 a.m. via email, all right? So you'll send me a PDF form and stuff like that's cool. If you're using like Cam Scanner or a program like that, it'll just take pictures of your work, put them into a PDF, send it off, and you're good to go, all right? The midterm itself will have 20 multiple choice questions where each question has 5 possible answers and only one question is right. There won't be 2 or something like that. There's also, there's also 4 short answer questions. I was thinking about 3 for a while, but there will be 4. 4 short answer questions where you show your work and stuff like that. The exam's due Friday. When I return the midterm to you, as well as having your score there, there will be a summary sheet at the end. And the summary sheet is just how you're doing in the class as of today, all right? You can always check with the grades online, but this will be a little bit fancier way to see how you're doing. And it'll also say, like, if you're missing a lab, make sure you get it in, that kind of stuff, pretty chill. There's a sample midterm exam online. And if you have time between now and next Wednesday or so, I do encourage you to check it out. The answers to the exam are at the very end. So if you go through and take the exam, you can see how you're doing. If you get the answers as listed, pat yourself in the back and move on. On the other hand, you don't get question number 17, and that would be a time to check it out. If you don't get it, let me know, and I'm happy to help too. In the old days, it used to always be Scantron based. That's not going to happen this term since everything is different. So this is all online. When you're doing questions for these online exams, make sure you show your work, even the multiple choice questions, all right? Put it right next to the question so I can see it easy, all right? If you just turn in an answer and there's math involved, then that could be worth some point deduction. So just show me your work, all right? That's totally appreciated. But otherwise, I mean, it should be pretty cool. Questions, this kind of stuff. Okay. Yeah.
And it's just under the same format as the quiz. We go home, print it out, and then we can work through it.
That's what I highly recommend. You bet. That's right. Just if you print it out and stuff like that, then you can just work on it and send it like that. That would be fantastic. Keep that. There is an integrity statement on the front page. This is something else. This is just saying that you're not cheating in the class. Integrity statements are something that I think is really important. It's your word of honor to me, all right, that you haven't cheated, you haven't gotten aid and stuff like that. Will I ever know if you did or not? No, of course not. But I believe in the sense of us communicating, being honorable to each other. I may be a little old-fashioned, but anyway, citing the integrity statement is something that's really important. So make sure you sign that and stuff. Just says that, at least on paper and stuff, you're not going to do it. And that's really cool. If you have questions on this kind of stuff, anytime you want to ask, it's totally legit. I know for everybody in this room, this will be, I think, the first time you've had an exam from me. And of course, it's always different when you're with a new instructor. So I want to try and minimize those kind of things as much as possible. What we're going to do now is just go through a series of questions that are kind of like the multiple choice questions, all right? There'll be a question with 5 possible answers. And what I'll do is I'm going to wait a little bit to answer the question. And what I'd like you to do is try it yourself, all right? And you can work with your partners next to you if you want, or just do it by yourself. So pretend like you get what you think the right answer is. And then after a few moments, I'll talk about what the actual answer actually is. I'll show you the steps and stuff in order to solve it. Any questions? All right, let's do this then. All right, so here's the first sample question, all right? And this might look familiar to something we talked about a little bit before, but the goal here is we're trying to figure out which metal is our unknown, all right? And to figure that out, you can see here, here's like a graduated cylinder like we used in the density lab. And we started with 10 centimeters cubed of water, and we put this piece of metal in, and this volume went up to 22.3 centimeters cubed of volume of water. And the mass of the metal, 33.2. See if you can find the identity of this unknown metal. And of course, by identity, what's probably going to happen here is you'll first find the density, and then you can use this little table to see which density is most likely your metal. But see if you can do that. And after a little bit here, I'll show you the answer and talk about how I would have solved it. If you have your calculator, you're welcome to try it. If you don't have your calculator, you can just fill in the work and stuff, and we'll talk about how that works later.
In terms of what materials are we allowed to use? Like, are we allowed to use periodic table? Is that just about it?
You can honestly use any resource you want, man. On a thing like this, I'm not going to try to hide or protect your browser or whatever they do. So it is very open note and stuff like that. So good. The important thing is that you should have everything you need from the materials we've studied. All right, but that being said, the Khan Academy is available for you too. Good. COVID. I mean, excuse me. Okay, has everybody had a good spot to talk about this? Everybody working? Okay. So this problem asks ideally, of course, for the identity of the metal, but honestly, it's just a question about density. And Archimedes Principle is the fancy thing for the displacement method, where normally when you add one thing to the other, the volumes are additive. So if we started with 10 milliliters of water, then the final volume will represent that 10 milliliters plus so many milliliters of the metal to make 22.3 milliliters. And by the way, I am using milliliters here, even though it says centimeters cubed. Remember, a milliliter and a centimeter cubed are the same. And milliliters are usually used for liquids, centimeters cubed for solids, but they are interchangeable. So in this question, you want to solve for the density and then compare your density to the table. So density is mass, which is grams usually, divided by volume, which is milliliters or centimeters cubed. And you want to take 22.3 minus 10 to get the volume of just the metal. You want the mass of just the metal divided by the volume of just the metal. And in this problem, when I calculated it, it came out to be 2.70. So again, I got that mass of the metal divided by the difference before and after when we added it to the water. You could, of course, use 12.3 right here instead of the difference. That's fine. But the density was about 2.7. And if you look, density looks a lot like this one right here. So I think we have aluminum. Questions on that? Awesome. Okay, here's another question. These are some locations on the Earth: 29 degrees Celsius, 45 degrees Fahrenheit, and 256 Kelvin. And this question says, what's the order of increasing temperature? So that means coldest first and hottest last. Now, obviously for these are three different types of temperature conversions. And the one that I would absolutely give you is the Fahrenheit one, because we're not going to do a lot of that. Fahrenheit, 1.8 times the Celsius temperature plus 32. And that's one on anything from me, whether it's in class or out of class, I would always give you, all right? And what I would do for the Fahrenheit temperature up there is I would convert that to Celsius. So I would put 45 in for right here. This would be like your X you would solve for, all right, and you get the Celsius. The other thing you might need then is the Kelvin temperature. The Celsius temperature equals the Kelvin temperature plus 273.15 minus. Yes, minus, sorry. Getting too excited. Celsius values can be negative. Kelvin temperatures will never be negative. So here, if you take 256, subtract that, that would give you the Celsius. So I would try and work towards the Celsius units here, and then convert around there. See if you can find which one of these, then, is the order of increasing temperature. And we'll talk about it here in a little bit. looks like people doing pretty good. Anybody still working? All right. Before we talk about the math, sometimes I like to talk about my hand-waving ways of understanding these problems, all right? And in my hand-waving world, all right, you can see right here that Kelvin minus this number is going to give you Celsius, and 256 Kelvin is less than 273. So 256 is going to give you some negative Celsius temperature, all right? Or it'll be a number that's pretty small. So I'm going to guesstimate then that Kelvin's the coldest one here. This is definitely 0 degrees Celsius is where water freezes, okay? So this is definitely warmer than that. I know because I grew up in Gresham that 32 Fahrenheit is where it begins to freeze. Oh, come on, cancel school. No, I mean, I used it as a scientist and stuff to realize that, seriously, 45 degrees Fahrenheit then would be warmer than that. And 256, which is lower than 273, would be negative Celsius. So I'm going to hand wave it and say I think 256 is lowest. I suspect this is close to 32 Fahrenheit, so I'm going to guess this is next, and this would be the warmest. So that's my unofficial way of figuring this problem out. But the very best way, of course, would be to go here. And what I would do is I would try to get to a common unit. And Celsius is a good halfway point between Fahrenheit and Kelvin. So Kelvin 256 minus this will give you some number in Celsius, but it's a negative number like we talked about. Now the Fahrenheit's a little trickier, but not that bad. 45 equals 1.8 times Celsius plus 32. To solve this problem, you first subtract 32 from both sides. Then you want to divide all of that by 1.8 or 9/5. Either way is totally fine. And if you do all of that, here's the actual steps involved. So again, 256 Kelvin minus 273 comes out to be this negative 17 degrees Celsius. And here's how I did the other part, the Fahrenheit to Celsius. So I took Fahrenheit, subtracted 32, then divided by 1.8, and it is positive, but it's not that much above a freezing point of water. So 7.2, the Fahrenheit right in the middle. The Kelvin is the coldest, and the Celsius here would be the warmest one. And I bring this up because sometimes you can kind of think around these problems. The math is always good. You can always go to the math, but sometimes you can kind of get around it by thinking about things which may be somewhat common in your world. Any questions on that? If you have an app on your phone or something like that, you can double check these kind of questions too. Just convert the values over from one unit to the other. Again, Celsius is a good way. If you didn't use Celsius, then there'd be 2 steps to go from Kelvin to Fahrenheit, or 2 steps to go from Fahrenheit to Kelvin. Lazy chemists. All right. Here's a similar kind of problem, but this time it's with lengths, all right? These are all lengths because they're meters, all right? But you see here there's millimeters, centimeters, et cetera, I'd like you to put these in increasing size, so smallest to largest. So again, same kind of problem, you just need to convert over. Now for this one, you're going to need some metric prefixes. Centa, 10 to the minus 2, milli, 10 to the minus 3. And because these are all lengths, the base unit is meters. You could say a centimeter, 10 to the minus 2 meters, or a millimeter, 10 to the minus 3 meters. See if you can use this information to figure out this problem. Looks like people are doing good. Sweet. All right. First of all, right off the bat, answer A can't be right because even if you don't know anything about meters and centimeters, etc., 2.3 is not less than 1.125. So answer A doesn't make a lot of sense here. But the other ones you have to do some conversions. And again, what I would do is just convert them all to meters. So if you have 9 centimeters, then and a centimeter is 10 to the minus 2, it's like 9 times 10 to the minus 2. So you'd move the decimal point over to the left. So 9 would be 0.09 meters. And with millimeters, you would multiply by 10 to the minus 3. You'd move it over to the left 3 times. So that would be 0.215. So if you think about 0.09, 0.125, 0.215, and then 2.3, then the answer comes out to be D. All right, D here is the best answer. This is 0.215 meters, that's bigger than the 0.125 meters. If this was grams, you do the same thing. All right, same metric prefixes, you would just have milligram equals 10 to the minus 3 gram, stuff like that. Any questions on that? Sweet. All right, which of these is not an isotope of element X? Now, I'm not telling you what X is, but I will say that Z is 9. So see if you can use this information, figure out what the heck Z is, what Z of 9 is, and then figure out which one is not an isotope. Up here on the board, I wrote the 3 isotopes of hydrogen. The first one, hydrogen 1, is also known as protium. Hydrogen 2, also known as deuterium. Hydrogen 3, also known as tritium. They all have the same number of protons, which is the atomic number. And that's what the Z is right here. So they all have the same number of protons, but notice how the upper left-hand number, the mass numbers, are different. That's because thanks for playing, isotopes have different number of neutrons, but the same number of protons. So for this one, all right, if Z is 9, that means all of the lower numbers have to be 9. All right, those will all be the same element. The top numbers, 22, 21, 18, 19, those are different. Those are the mass numbers of neutrons. But number B right there, that's not an isotope. That's a whole different element. So if you know and stuff that X is 9 right here, one thing you could do is just look it up on the periodic table. And number 9 over there on the upper right, that's fluorine. all right? So the X here, I made it sound kind of mysterious, but actually all it is fluorine. These are E, D, C, and A. Those are all isotopes of fluorine. This would be fluorine 19, fluorine 21, et cetera, et cetera. This one, though, is not fluorine, all right? It has a different atomic number. What element would that be? Neon. Well done. And again, who knows what X is, but 10 is the answer. 10 on the periodic table over there is Ne, so that would be neon. So B is not an isotope. That's a whole different element. Questions on that? Sweet. So here's what I'd like you to do. One of those statements is most applicable here. And it says, what's the composition of a neutral atom of iron 58? And see if you can pick which one you think is the best answer up there for iron 58. Back over here with the hydrogen isotopes. All right, the lower left number, that's the atomic number, and that's the number on the periodic table for hydrogen. And the atomic number and the symbol are always related. So one is hydrogen, hydrogen is one. These upper numbers, like we said, are the mass numbers, all right? And the mass number is important too. Like we would call this hydrogen 3, hydrogen 2, stuff like that. How would we find the number of neutrons in hydrogen 3?
Subtract the top number.
Absolutely. Top number minus bottom number. So this one has 3 minus 1, 2 neutrons, 2 minus 1, 1 neutron, 1 minus 1, 0 neutrons. All right? So neutrons, top minus bottom. This is the number of protons, the atomic number. And if these were neutral hydrogen atoms, how many electrons would there be? 1. That's right. Protons and electrons have to be equal for them to be neutral. All right? So in this problem, the 58 is like the 3 right there. It's the mass number. All right? We need the lower left-hand number here for iron 58. And how do we find that lower number? Periodic table. Most of the time in chemistry, the answer is the periodic table. But anyway, yeah, periodic table. So there's iron, and iron Fe is number 26. All right. So what we have here then is we would have 58 in the top, 26 in the bottom, and Fe would be right there. So iron here is going to have 26 protons. All right. So when we go through these different lists, you want to find one with 26 protons. Doesn't have 32 protons or something like that. If it's neutral, the electrons and the protons are going to be the same. All right? So neutrality means protons and electrons are the same. Protons are positive, electrons are negative. The only piece here we don't have then is the neutrons, but that's the top number minus the bottom number. So 58 minus 26, 32. Answer B here would be the best answer. So neutral means protons and electrons are equal. Protons comes from the atomic number on the periodic table. So 26 is protons and electrons. And then there's no direct neutron number, but top number minus bottom number will give you number of neutrons. Questions on that? Cool. Here's an element E. Again, who knows for sure what it is, doesn't really matter. But anyway, we have some abundances, all right? There's 3 abundances for the 3 different isotopes. There's a couple different ways you can answer this, but using this information, make a prediction which of these is the most likely atomic weight, the most likely average mass, all right? And again, we've got 72, 73, and 74 right here. Using that information, see if you can predict which one is the most likely atomic mass. This would be the red numbers on our periodic table. All right, how they got a red number for this element. On a problem like this, there's a couple different ways you can do it. This is the number line I talked about in Chapter 2, Part 1. And the 72, 73, 74 represent the mass numbers, those 72, 73, 74 of these values. And if you have almost all 72 and not a lot of 73 and 74, then the average will be closer to 72. On the other hand, if you had a high percentage of 74 and not much of these, then the average would of course be closer to 74. And if you had mostly 73 and not a lot of the outliers, then the average would be somewhere around there. Now you can see by these percentages that you have a lot more 72 than you have 73 and 74 combined, all right? So I would predict that the percentage would be in this region right here. It's going to be more than just 72 because it's not 100% 72. On the other hand, we have more than 2 to 1 72 relative to the other ones, so it'll be closer over here. So hand waving, all right, because this isn't 80%, it's 50%, I would guess it's probably going to be B, all right? That feels right to me because, again, we have more 72 than the other ones, but on the other hand, it's not like 90% 72, which would make it something like this. And for some of you, that'll be cool, but you can also do it the quote-unquote math way. And the math way would be to take the mass number and multiply by the decimal version of the percentage. So 72 times 0.545. And you would add that to 73 times 0.156 plus 74 times 0.299, et cetera, and that's just as cool too. But either way you do this, all right, it should come out to be about 72.8. So either way is fine, all right? You can think about it in terms of percentages and hand waving. You can also, though, just do the math way, and that's legit too. This little symbol right there means add up all of them. So it means add up all of the abundance times the mass values. That's what's happening right here. And again, it comes out to be about 72.8. This is how the red numbers are born on the periodic table. They didn't just come out of a black box, all right? There's like a reason for them. Questions? Okay. The question here is which of these is probably not likely to form, all right? There are some metals, and these are all metals on the periodic table, where the charges are known all the time. There are some metals that we know can form, but they're variable charge. We may not be. But I'm asking you here to tell me which one of these is most likely not to form. All right? So think about that here for just a little bit, and see if you can figure out which one of those would be very unusual. Okay, so these are all metals. And let's just review real fast. The metalloid line, the kind of cross thing there on the upper right side, separates the non-metals, the upper right, from the metals on the left. And as we've seen now, if the metal charge is known, you can then combine it with the non-metals, which always have fixed charges, to figure out formulas. And of all of these metals to the left of the metalloid line, most of them are what they call variable charge metals, and we don't know their charge at all. We need other information, all right? However, there are some fixed charge metals where we always know their charges, and that's group 1A on the far left, group 2A right next to it, and those are positive 1 and positive 2. And then there's also those weird 6 elements kind of on the right, which are the stairs. Aluminum, gallium, indium, positive 3, zinc and cadmium plus 2, and silver plus 1. So if you look at this list then, like sodium is a group 1A metal, that's positive 1, that seems legit. Aluminum and zinc are both part of the stairs. Positive 3 aluminum seems legit because it's in the third step. Zinc and cadmium, second step, so they should be positive 2. Now iron is a variable charge metal, and that one's going to be harder to predict, but it should be positive, and that doesn't seem out of control because it could be positive 3 or it could be positive 2. It doesn't seem that it won't form. But what's wrong with magnesium right there?
It's the close charge at all.
Exactly. It's in the positive 2 column. And magnesium, for us, never is going to be positive 3. All right? Magnesium, for us, always positive 2. Everything in that group is going to be positive 2. So we would not predict magnesium plus 3 to form. We wouldn't predict magnesium plus 1 to form. We would only predict magnesium plus 2. And that's the value of the fixed charge metals. So iron, we couldn't say this for. Iron, for example, can be positive 3. It can be positive 1. It's a variable charge metal. But if you have a fixed charge metal that isn't for what it's supposed to be, those are the ones you'd say, no, that's not going to happen. So magnesium we would not predict to be a positive 3 metal. Any questions on that? Okay. This is a good place to take a break. It's about 10:55. Come back here around 11 o'clock. We'll take this stuff on a little bit further.